Alright, I hope everyone's doing alright today. And hope that was a good resolution of the issues with the exam, that it becomes a take-home test. I think that it will overall help everyone. And again, make sure that you get that turned in by tomorrow night, Wednesday night. That way, I get those graded. I don't know when. Probably over the weekend, I would say. But I can't imagine getting it done any sooner. Because I have a whole other batch of tests being turned in tonight that I got to deal with. So, for all three of my statistics classes. So it's going to be a crazy couple weeks for me. Just as crazy as for all of you, I imagine. Anyway, so today we're going to cover the material we need to out of Chapter 10, which is on polar coordinates and polar graphs and area inside a polar curve. On the review, there's going to be a lot of stuff from Chapter 10 that we just don't need to do. I will be sure to point that out on Thursday when we go over the review. So hopefully that will be informative. Yeah. Alright, so Chapter 10, talking about polar coordinates and polar graphs. There we go. Okay. So the idea of polar coordinates is an alternate coordinate system to rectangular coordinates to identify the same points. We're giving a designation to the same coordinate on the plane. It's just a different way of ordering it, because when we look at rectangular coordinates, we could have a point here which is identified as 4, 3. So we base it on the horizontal component x and the vertical component y. How far is it displaced horizontally versus the vertical displacement. When we look at polar coordinates as an alternative, we're going to be looking at that same coordinate, but instead of using horizontal distance and vertical distance, we use distance from the origin, which we'll call the radius, r, and we'll use the angle with the what would normally be the positive x-axis. We'll use the angle theta to describe the location of this coordinate, which will be r comma theta. Okay. So we're actually talking about the exact same point on the plane, but we're looking at two entirely different methods for identifying that point. And what polar coordinates do is it opens up more possibilities for us. When you get into Calculus 3, you'll look at, even here, when we look at our areas, we see a greater variety of integrals that we can solve with polar coordinates that we couldn't do when they were in rectangular coordinates. So we can find different areas, find areas of different shapes that we couldn't normally do because they're not actually functions in rectangular coordinates, but they're completely valid functions in polar coordinates. And so, even just a basic circle, finding that area, well, ideally we would use geometry, but finding the area in polar coordinates is way easier than rectangular coordinates, and similar shapes to circles and other enclosed figures like that. And so when we get to 3D graphing in, I believe it's chapter 15 in Calculus 3, or maybe 16, I don't remember. It actually opens up a lot more possibilities as far as what types of things we can find volumes of, and so on. Anyway, excuse me. So we want to start off with the conversion to polar coordinates from rectangular. And we can actually find this coordinate for 4, 3 in polar form. Sometimes, to avoid confusion, we may give our coordinates a little subscript, like this is a rectangular point, this is a polar point. Especially if we're using them together, it's nice to distinguish which one's which. Although a lot of the time our theta will have like a multiple of pi in it. It's usually, in that case, a little bit more apparent that it is a polar coordinate than a rectangular coordinate necessarily. But if we're working with trigonometry, it could go either way. So R we define as the square root of x squared plus y squared. And I think that was pretty straightforward, because if you superimpose x and y onto this graph, R is basically the third side of that right triangle, so it's basically the Pythagorean theorem that we're using to describe that. And similarly with theta, we have a right triangle here, so if we think of theta, what function relates it to y and x? That's the opposite, that's the adjacent side to angle theta. So that's tangent. So tangent of theta is y over x. So we would say theta is inverse tangent of y over x. We do have to be a little bit careful about theta if y or x is negative, because if one or both are negative, that putting us into a different quadrant. Let me give you a more precise definition of theta. It's equal to inverse tangent of y over x if we're in quadrant 1. But if we're in quadrant 2 or 3, we have to add pi, or normally we'll write theta as a measure in radians. We could use degrees, but radians works because now we can use it in other applications after we get a value. And then if we happen to be in quadrant 4, then we need to add 2 pi to that inverse tangent value. Oops. There we go. So that gives us a little bit more of an accurate representation of the value of theta. Just in quadrant 1, like this one is, we can just simply do the inverse tangent. But if we happen to be in one of the other quadrants, then we need to adjust accordingly. Alright, so if we wanted to convert 4, 3 in rectangular coordinates to a polar coordinate, well, 4 and 3, if we take r equals square root of 4 squared plus 3 squared, that's 16, and 9, that makes 25, so square root of 25. So So r is equal to 5. And for our theta, theta will be inverse tangent. Now I'm way over to the left. Okay. Inverse tangent. And we do y over x, so that'll be 3 over 4. And making sure we're in radians in the calculator. Yeah, I was in radians already. Inverse tangent of 3/4, or 0.75 if you like. We end up about 0.64. So we would say 4, 3 in rectangular coordinates is the same as 5, 0.64 in polar coordinates. These identify the exact same location, but it's a different nomenclature that we're using. Because when you look at rectangular space and the way that we assign values, a rectangular plane, not space. Space is 3 dimensions. With rectangular coordinates, we basically have a series of lines vertically and horizontally. It's not the greatest plane I've ever made, but we count over and up, or left, up, and down, right, whatever, and you get the location of our point that way. Whereas in polar graphing, we think of the radius as concentric circles at the origin. And the angles as lines going through the origin. Like so. Okay. So this would be 0, pi over 6, pi over 4, pi over 3, pi over 2. It's almost like a unit circle, actually. It's exactly like a unit circle when we look at the angles here. 2 pi over 3, 3 pi over 4, 5 pi over 6 pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, yeah, 3 pi over 2, let's see, 5 pi over 3, 7 pi over 4, and last one's 11 pi over 6. And what we would do is we'd count out from the circle 1, 2, 3, 4. So each of these, at the center, of course, is a distance of 0 from the origin. This first circle is a distance of 1, distance of 2, distance of 3, and distance of 4. Now, if we look at a certain coordinate, let's say we're looking at this coordinate right here, call it point A. So point A is on the curve, or on the angle pi over 2 at a distance of 1, 2, 3 from the origin. So it'd be 3 comma pi over 2. Point B right here is distance of 2 from the origin on the angle 7 pi over 6. And point C over here is at an angle of 5 pi over 3 at a distance of 1, 2, 3, 4 from the origin. 5 pi over 3. Okay. Here's an issue that we encounter with polar coordinates. Not really an issue, but an aspect. And that is that there's actually an infinite number of ways of defining each coordinate, because this is 3 comma pi over 2, as we said. But if we make another rotation around the circle, we can add 2 pi to the angle, and we can call it 3 comma 5 pi over 2. So that's a full rotation plus another pi over 2, which gets us to the same location. So there's infinite ways we can do it. We could also go backwards. So like point B, if we start from 0, go forward to point B, that's positive 7 pi over 6 radians. But if we go backwards to point B, that's negative 5 pi over 6 radians. Okay, so we could, depending on which way we go around the circle, that gives us multiple ways of defining it. So it goes forwards and backwards. And the last thing we can do is, angle point C here is on this angle 5 pi over 3, but 5 pi over 3 is opposite of 2 pi over 3. So what we could do is we could go around to an angle of 2 pi over 3, but go in a radius of negative 4, which goes 1, 2, 3, 4, the opposite direction from 2 pi over 3. So negative 4 comma 2 pi over 3. Now, these are not unique to each of these. Like, we can apply this same concept here or here. This concept applies to any of the other two. This concept applies to any other two. Excuse me. It's a little cold in here this morning. Alright, but those are all different ways that we can represent coordinates in the polar plane. So we have kind of our conventional way, which is a positive radius and an angle between 0 and 2 pi. That's more of the conventional way of thinking it, but we can make an extra rotation around the circle to get us the same coordinate. We could go backwards from 0 instead of forwards, get us a little bit different coordinate. Or we could go to the positive angle and then go in the opposite direction. This is the trickiest one, I think, or the strangest one. That we could come around to 2 pi over 3, but then count negative 4, which goes in the opposite direction. Anyway. So that's the different ways that we can label polar coordinates on a plane. Actually, I think it's in my office. I didn't bring it with me. I have a polar whiteboard, like a tabletop version, which would be perfect for this moment, but of course I don't have it with me. But it has a polar graph just printed onto the whiteboard, so I can just draw on it with a marker. Gosh, if I had thought about that, I would have gone to college and picked that up. Sorry about that. Anyway. Oh, that would have been way easier in this situation. Anyway, we'll press on without it. So that's graphing, and that's how we convert. Now, we talked about conversion from rectangular to polar. So rectangular to polar. We said that r is the square root of x squared plus y squared. And we said theta was inverse tangent of y over x. Now, I'll put an asterisk there because we know that it's a little bit more than that, depending on which quadrant theta is going to be in. But that's roughly what's happening. We also want to look at how to convert from polar back to rectangular. And so this one's actually a little bit easier. X is r cosine theta, and y is r sine theta. So for those of you in physics, that might look familiar. Certainly there is a connection to what we're doing here versus what you might be doing in that class. Anyway, so if we wanted to take this coordinate 4 comma 5 pi over 3 in polar and convert it to rectangular, so x would be 4 times cosine of 5 pi over 3. Could have picked an easier point. A would have been a lot easier. Oh well. Goodness. Well, A was very clear what point that is. If we look at A, we can just see that's 0 comma 3 on the rectangular plane, because it's 0 left or right and then 3 straight up. That's actually pretty easy to convert A. Yeah, this one's a little bit more tricky. 5 pi over 3 puts us in the 4th quadrant. But 4 times cosine of 5 pi over 3 is the same thing as 4 times cosine of pi over 3, which is 4 times 1/2, I believe. Yeah. So that'd be 2. You can do that in a calculator if you want to. And then for y, that would be 4 times sine of 5 pi over 3, which is negative root 3 over 2. And so times 4 is negative 4 root 3 over 2, so negative 2 root 3. So that would be the coordinate in rectangular coordinate system. Okay. Now, not only can we change individual coordinates from one system to the other, we can also change entire equations from one system to another. And this is where our transition formulas here help. Like polar to rectangular, this will actually let us change functions in x and y to functions in r and theta. And typically, when we have a polar function, we write it as r equals a function of theta. That's worth mentioning as well. So polar functions are written as r equals a function of theta. So even though we say it's r comma theta as a coordinate, we actually use theta as the independent variable and r as the dependent variable. It generally works better that way than the reverse, because the reverse is much harder to do on a regular basis. Anyway, so if we take a function like y equals 3, which is a line, and this is rectangular. Y we know is r times sine theta. That's equal to 3. And we solve for r, which is 3 over sine theta, which is the same thing as saying r is 3 times cosecant theta. Now, let me graph r equals 3 cosecant theta for you real quick. It looks exactly like that. And I don't really know how to graph r equals 3 cosecant theta, but I absolutely know how to graph y equals 3. Y equals 3 is just a horizontal line through 3. So when I graph r equals 3 cosecant theta, the graph is equivalent to the rectangular graph. So we're actually describing the same line, it's just one's written in rectangular coordinates and one's written in polar coordinates. Now, if we wanted to graph a circle like x squared plus y squared is equal to 4, that's the equation of a circle with radius 2. Close enough to a circle. That would be... Now, there's a shortcut we can use here, because we know x is our cosine theta and y is our sine theta. So we could do it that way. But if we square that, we get r squared cosine squared theta plus r squared sine squared theta equals 4. You can factor out the r squared, so it's cosine squared theta plus sine squared theta in parentheses, but we do know cosine squared theta plus sine squared theta, that's one of our Pythagorean identities, that's equal to 1. So this is 1, then we just have r squared equals 4, or we could actually say r equals 2. Normally we wouldn't be able to get away with saying r equals 2 only. Usually we'd want to say r equals 2 or r equals negative 2. They actually describe the same circle, which is kind of odd. Yeah, r equals 2 is a circle, or every point that's a radius of 2 from the origin, which perfectly defines a circle. So we can basically use x squared plus y squared equals r squared as kind of an identity that we can apply here in certain scenarios where we have like circular sections or similar. Really has to be, well, it really does have to be a circle that we can apply that, but it's useful in that scenario. And that goes back to our formula here. We said r is the square root of x squared plus y squared. Basically, if we square both sides, r squared is x squared plus y squared, and that's an easy transition. Okay. Let's look a little bit more at polar graphs. So if we said r equals 3 or r equals any number, for radius, that's just telling us how far it is from the origin. But that will always be a circle. Now if we had theta equals to a number, let's say theta equals pi over 4, then that's just a diagonal line with an angle of pi over 4 to that positive x-axis. So r equals a number is always a circle, that distance from the origin. Theta equals a number is always a diagonal through the origin that has the correct angle here. Whatever angle theta is equal to. And again, we could go, we could say like 9 pi over 4, which would be the same thing. So we could add 2 pi to that, and this would also be 9 pi over 4. We could subtract it from the opposite direction, which would be negative 7 pi over 4. Or we could even go around to this angle, which is 5 pi over 4. All three of those describe the same line. So it's really the same reasoning that we were using when we were talking about the individual points. The same applies to functions, so at least when we have theta involved like this. Now, if we have something like this, r equals theta, that means that the distance from the origin is equivalent to the angle that it makes to the axis. So we start at 0, 0, because if theta is 0, then r is also 0. But we think about it, okay, here's pi over 4, here's pi over 2, here's 3 pi over 4, and here's pi. Okay, pi over 4, we have a value associated with that. Pi over 2, we have a larger value associated with that. 3 pi over 4, there's a larger value. And pi, there's a larger value. So we end up with what is an increasing spiral. And so that just keeps going, because the more we go around, the larger our angle gets, the further we get away from the origin. And that actually works both ways, because if we go to a, this is going forward, if we go to a negative angle, then we're a negative distance away, so we're on the opposite side, so we end up drawing this curve on the opposite side, and it keeps spiraling out in the opposite direction as well. But yeah, that's r equals theta. It's kind of a weird one. Notice this would not be a function in polar coordinate or rectangular coordinates, but it's absolutely a function in rectangular coordinates. Sorry, I got it backwards. It's not a function in rectangular, but it is a function in polar. Now, anything more exotic than these takes a little more work. Now, for instance, if we said we want r equals sine theta, I might even say 2 times sine theta. That actually works a little bit nicer, I think. And it helps us illustrate a certain point also. R equals 2 sine theta. What we would do here, if we wanted to sketch this graph, or what we could do, is first of all, make a t-chart for theta and for r. Pi over 4, then pi over 3, my bad. Pi over 2. 2 pi over 3. 3 pi over 4. 5 pi over 6 would be next. And then pi. And then once we establish the pattern with those, I'll just go by pi over 4, so that'll be 5 pi over 4. 3 pi over 2, 7 pi over 4, and then 2 pi. Okay. So sine of 0, 0. Sine of pi over 6 is 1/2 times 2 is 1. Pi over 4 is root 2 over 2 times 2 is just root 2, which is 1.414. Sine of pi over 3 is root 3 over 2 times 2 is root 3, which is, what is that, 1.76? Square root 3. 1.73. Pi over 2, sine of pi over 2 is 1 times 2 makes 2. 2 pi over 3 is root 3. Root 2, 1, 0. Negative root 2, negative 1, negative 2, negative root 2, back to 0. So we have all those coordinates to plot. I'm going to draw 2 points on each axis because the largest value we have over here is 2, so that's as far out as we may go. And so, very lightly, I'm going to try to draw in angles for pi over 6, pi over 4, pi over 3. So we start at 0, 0. We get pi over 6, comma 1. Now, 1 is right here, so pi over 6, comma 1 is kind of in the intersection of that circle and that line for pi over 6. That's how we visualize that. 1.4, we think about where 2 is now versus 1. I didn't draw those in a great unequal scale there. Well, oh well. So 1.4 is a little bit less than halfway between. 1.73 is a little bit closer to 2. And then we get pi over 2, comma 2. Okay. Repeat over here. At 2 pi over 3, we have root 3, which actually should be the same height as this other one I drew, but I think I got the angle wrong this time. Or not equal. Sorry about that. 3 pi over 2, we have root 2. And then at 5 pi over 6, we have a value of 1. And then we get back to 0. So we draw in what's happening there. And what do you know? We've drawn a circle. This is actually a perfect circle that we've drawn, or that this graph would describe. But it's not a circle centered at the origin. It's a circle centered at, it basically sits on top of the axis. So when we have r equals sine theta, that would be a circle of diameter 1 on top of the origin. 2 sine theta is a circle of diameter 2, as we see here. 3 sine theta would be a circle of diameter 3, again sitting right on top of the axis, and so on. Now, you might say, well, we've only graphed up to pi 0. What do these other points do? Well, after we get to pi, we end up graphing the same coordinates over again. 5 pi over 4 is over here, but it's over here, but it goes when it has a negative r. It means we're pointing this direction, but we count the opposite way, so we come back to that same point again. 3 pi over 2, we go. We're looking. 3 pi over 2 is straight down, but we count negative 2, which goes 1, 2 the opposite direction. 7 pi over 4 over here counts negative root 2 the opposite direction, and then 2 pi back to 0. So we actually, in the process of going from 0 to 2 pi, we've drawn this circle twice. Okay. Excuse me. And so that happens with a lot of these graphs. So, like 0 to pi and then repeating, that's what sine does. Cosine, we would take the graph from negative pi over 2 to pi over 2. And then from pi over 2 to 3 pi over 2, it would repeat. So, similar issue there. Now, what if we wanted to graph 2 cosine of theta? What does 2 cosine of theta look like? Well, if 2 sine of theta is a circle, then you can bet 2 cosine of theta is also a circle. But it's oriented differently. Because 2 cosine theta would now be to the right of the origin. Wow, that's not a great circle. And so that is a circle with diameter 2. Notice that's not this diameter, not radius that we're talking about. But now it sits on the right-hand side of the origin rather than on top of the origin. Now, after that, things start to get a little weirder. Those are like our basic ones. What if we said r equals 1 plus cosine theta? Now, adding 1 is a different matter than multiplying by 1 or 2 or whatever. So again, we're going to make a t-chart here just for demonstration purposes. Let's see, for cosine, I believe we want to start at negative pi over 2 and count up from there to positive pi over 2. So I think we'll do that. It changes from one function to the other, but I think that's correct here. After negative pi over 2 is negative pi over 3, negative pi over 4, negative pi over 6, 0, and then pi over 6, pi over 4, pi over 3, and pi over 2. So negative pi over 2, cosine of negative pi over 2 is 0, plus 1 makes 1. Cosine of negative pi over 3 is 1/2. Plus 1 makes 3/2, or 1.5. Negative pi over 4, cosine of that is root 2 over 2, plus 1. 1 plus root 2 over 2, which is, what is that? 1.707, 1.707, yeah. Negative pi over 6, cosine of that's root 3 over 2 plus 1. That's 1.86 something. And then cosine of 0 is 1, plus 1 makes 2. And then it repeats. 1 plus root 3 over 2 is 1.86. 1 1 plus root 2 over 2, which is 1.707, 1.5, and 1. Let's try this again. These are all positive values, so I may have to graph more than that. So, let's see, let's mark out 2 units and try to be a little more precise with my markings this time. It worked out last time, though. So negative root 2 is this way, because this is 0, so this is negative pi over 2. This is positive pi over 2, because we count positive is counterclockwise and negatives clockwise. So at negative pi over 2 we get a value of 1. But we are going to have to get the rest of those values though on this side. Negative pi over 3 we get 1.5. Here. Negative pi over 4, we get 1.707. Negative pi over 6, negative 1.86. And then, or positive 1.86. These are positive values, sorry. And then 2 at 0. Now these are basically mirror images up here from the bottom. Okay. Yeah, we're definitely going to need this left half. Unlike just regular r equals cosine theta, r equals 1 plus cosine theta, it's a little more complex, so we need some more points. So we continue. It's after pi over 2. 2 pi over 3, 3 pi over 4, 5 pi over 6. After this, we're going to switch to the computer to do our graphing. I'm just showing you by hand right now. Because this is tedious, as you can already tell, I suspect. Pi, and then, was it 7 pi over 6, 5 pi over 4, 4 pi over 3, and 3 pi over 2. See, cosine of 2 pi over 3 is now negative 1/2 plus 1 is 0.5. 3 pi over 4 is negative root 2 over 2 plus 1. I'm going to do some calculator work on that one. 1 minus root 2 over 2. 0.29, which, or 293, which actually is, yeah, that makes sense. 5 pi over 6, 1 minus, that's root 3 over 2. So 0.13. And then at pi, we finally get to 0. And then these numbers repeat again, 0.13, 0.293, 5, and back to 1. Okay. Get our 45 degree first, and then get the other two. That's too close, but it's alright. I'm losing my edge here. Okay. That's better. You don't have to draw these lines like this. And what I'm illustrating, though, is kind of what's going on here. as far as how we measure coordinates and graph them, essentially. If you want to eyeball it, that's fine. And I think it helps to kind of, when we're learning, and especially to kind of superimpose it like this, where we can see exactly what we're graphing. All right. So 2 pi over 3, we got 0.5. 3 pi over 4, 0.293. Then 0.13, and then to 0. So it actually comes back here. Now, we can go ahead and graph in this other stuff. Kind of a spiral so far, but 7 pi over 6. Now we start coming out again. It's like that. It's a little bit deformed, but it's basically the correct drawing. This is what we call a cardioid, this particular graph. The reason we call it cardioid is basically heart-shaped. Not in the truest sense, but it's close enough that we call it a cardioid. Now, this type of graph, and I like to classify this type of graph in the form r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta. A lot of the time we can get away with just graphing 8 points instead of 16 like we did. 16? How many points do we graph? 1, 2, 5, 6, 7, 8, 9, 17. We can get away with graphing 9 points instead of 17. Usually what I do here is graph the 4 cardinal directions and then the 4 45-degree angle directions. I guess it's 8 points. Anyway, if we go from like 0 to 2 pi, though, 0 and 2 pi are basically the same thing, so it counts as 9, I guess. That way we kind of get a good idea of the principal directions that we're looking at. So if I had r equals 2 minus sine theta, for instance, I would say here let's graph this. Let's see, 0 pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. Sine of 0 is 0. Sine of pi over 4 is root 2 over 2. That's, what is that, 1.29. Sine of pi over 2 is 1. Sine of 3 pi over 4 is root 2 over 2, so 2 minus root 2 over 2 is 1.29. Sine of pi is back to 0, so that's 2. 5 pi over 4 is negative root 2 over 2, so that is 2.71. 3 pi over 2 is negative 1, so we get to 3, and then 2.71, and then back to 2. This time we need to go as far out as 3. But we're only looking at the diagonals and the cardinal directions. So 0, 2, pi over 4, 1.29, pi over 2, 1, 3 pi over 4, 1.29. Got it right there. Pi, comma 2. 5 pi over 4, 2.71, so we go out a little bit further. 3 pi over 2, comma 3. 2.71 this way. And then back there. So something like this. Now, this one doesn't go through the origin, so it's not a true cardioid. I think what we call this one is a dimpled lemison, which is, the nomenclature here gets a little crazy, I'll be honest. So up here we had a cardioid, and this is a dimpled lemison. Okay. I actually want to graph one more by hand because it's a fascinating graph. And then we'll go to the computer to graph these, and then we'll look at areas, which is another adventure entirely. But like I said here, with these graphs, where it's just like two, like a plus or b, a plus or minus b times sine or cosine, which is off screen, like these two types, these two definitions, which both of these graphs fall into that category here. These graphs, we don't have to necessarily pick all these points, we can just kind of pick these points, and that's sufficient. Now, this next one is a little bit more crazy. But crazy in a fun way. Maybe. Let's see, we just did a sine function, let's do a cosine function. No, I want to do a sine function. Sine is a little more interesting here, I think. Let's do 2 sine 2 theta. I like using multiples of 2, that way our root 3 over 2s and root 2 over 2s, those get a little bit easier to work with. Anyway. What I'm going to do, because we have 2 times theta, I'm going to count by pi over 8s. 0, pi over 8, pi over 4, 3 pi over 8, pi over 2, 5 pi over 8, 3 pi over 4, 7 pi over 8 pi. Let's see what that gets us. May not be enough. We may have to keep going all the way to 2 pi. Actually, I suspect we will go all the way to 2 pi, so I might as well do it now. 9 pi over 8, 5 pi over 4, 11 pi over 8, 3 pi over 2, 13 pi over 8, see, 14 pi over 8, 7 pi over 4, 15 pi over 8, and then finally 2 pi. And the reason I chose pi over 8 is because if we do 2 times pi over 8, that's pi over 4. So basically we're counting by pi over 4s as far as what's going to be plugged into the sine function. Maybe it's enough just to go to pi. We'll find out. sine of 0 is 0. This is sine of 2 times pi over 8, so it's sine of pi over 4. It's root 2 over 2 times 2 is root 2. Again, it's 1.7. No, 1.414. There we go. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. Times 2 is 2. Okay. 3 pi over 4 is root 2 over 2. Times 2 is root 2. Sine of pi, 0. Okay. Well, you can ultimately see that there's going to be a pattern here. We're going to go negative root 2, negative 2, negative root 2, back to 0. Positive root 2, 2, root 2, 0, negative root 2, negative 2, negative root 2, 0. Okay. Excuse me. Draw in our diagonals. We will need those. We also have the pi over 8s, which splits the difference between these. We need a radii at 1 and 2. Again, trying to equally distance these. Not perfect, but good enough. What happened over here? Actually, I think that's what happened on the bottom. Anyway, it's a little distorted, but we'll get the idea. Okay, so that's, anyway, don't have to do that. I think it helps me make a better picture, personally. So we start at the origin. Pi over 8, root 2. Pi over 4, comma 2. 3 pi over 8, root 2. And then back to 0. So what we've done is we've made a loop like that. Already very different than anything we've done. Then we continue. 5 pi over 8, we go negative root 2. 3 pi over 4, negative 2. 7 pi over 8, negative root 2. And pi back to 0. So we've actually made a similar loop down here. And so we continue. 9 pi over 8, which would be right here, out to root 2. 5 pi over 4, 2. 11 pi over 8, root 2. And 3 pi over 2 back to 0. Well, I think you can see what's going to happen in the last bit. We're going to get a root 2, we're going to get a 2, a root 2, and back to 0. And that's our graph. When we start multiplying theta by numbers here, it creates these flower patterns, basically. So if we did sine 2 theta, it's a flower with 4 petals. Sometimes we see this written called a rose, but it's not a rose. Mathematicians weren't exactly creative when they were doing this. It's more of a dandelion. Anyway, especially when you get to higher values. So if we did sine of 3 pi, we'd have 3 petals. Sine of 3 theta, sorry. Sine of 4 theta would have 8 petals. Sine of 5 theta would have 5 petals. And sine of 6 theta would have 12 petals. It turns out when we have an even number, it doubles the number of petals, but if we have an odd number, then we get an identical number of petals. That's kind of an interesting consequence there. I think what happens is with the odd numbers, it actually graphs over itself twice, whereas the even numbers, we actually get twice as many petals. Anyway, that's 2 sine 2 theta. 2 cosine 2 theta would basically be rotated 45 degrees, so the petals would be on the lines rather than between the lines. So it would be up and down versus diagonal. And if we were looking at how this graph was sketched, if we go through our progression of points, it actually makes one smooth line. Like so. And that's the great thing about it. It's just one continuous line, but knotted up into these loops as the way that the sine function evolves. Let's look at the computer now and do some more of these graphs using technology that does it much more quickly than I can do it by hand. Decimals. Hopefully we can see this okay. Now, we'll need the Greek letters. There we go. Data. I'm just going to copy and paste that so I have that available. Okay. So let's do r equals 1 plus sine theta. And that's our cardioid that we talked about before. Notice if we change that to a minus, it flips it to the opposite side. If we change it to cosine, rotates it again, and if we change that to plus, rotates it again. But all of those have identical numbers, 1 here and 1 is the coefficient. Now if we change this coefficient to 2, we get an inner loop. If we change this to 2, we go back to our cardioid, and then if we make this number larger, we get our dimpled limacon. So if this number is larger, we get a dimple limacon, but if this number is larger, we get an inner loop. And if the two numbers are equal, we get our more conventional cardioid. The same thing applies with sine just as well as cosine. It just changes orientation. This one rotates it basically. Okay. 2 sine 2 theta, which we just talked about. You can see what the graph looks like there. If we went to 3, okay, 3 petals, as said. 4 should have 8 petals. There we go. 5 petals. 6 would have 12 petals. 7 petals. 8 would have 16 petals, and so on. Now it looks a little more flower-like. Well, that's probably a little too many petals for a flower, actually. 4 might be a little more conventional, or 6. Or 9. Anyway. And we can change this number make it larger or smaller. Okay, the number on the outside is just kind of magnifying the size beyond a certain point, because notice that the tip of these petals are at 6, distance of 6 from the origin. You can see this top one right here at 6. So if we drop that down to 4, that's where it is. So 4 is really just the length of the petals here. Okay, the coefficient there. And if we change that to cosine instead of sine, it rotates. It's easier to tell the rotation. We're looking at 2 petals, or 4 petals, I guess, with 2 theta. There's sine. And there's cosine. And there, the cosine is in blue, and then the sine is in whatever that color is, red or green. I can't tell that at that magnitude. Anyway, and some interesting shapes. Now, we haven't really talked about tangent. Tangent theta is kind of crazy, to be honest. Zoom out. It's actually continuing to infinity in those directions, because the tangent graph can grow without bound. Now, if we change the domain to 4 pi, actually, I can go up to 10. No, it still does basically the same thing. Yeah, it's not going to do anything interesting. If we look at secant theta, that's a vertical line. 4 times secant theta just moves it out to 4, 5, 6, etc. If we look at cosecant instead, that should be horizontal. There we go. And you saw for a second the spiral. Let me get. There you can see a little bit better. I guess it didn't have to go that small. There we go. We can see the spiral that's created. And see under here, this is the domain they're using, 0 to 12 pi. So we're actually making multiple rotations, but it will just keep going beyond that and just getting further and further away. We could try squaring the pi, and it would accelerate more rapidly. Now I might need to put that 0 there. So we get a little bit different spiral happening with the square, but it's still largely the same. Anyway, there's a lot of different things we can do with these graphs, but again, technology does a lot of this stuff for us, which is great. So we don't have to do it by hand all the time. It's nice to understand how to do it by hand, but again, that's not the entire story. It's nice to have the technology to lean on in that situation. I think that's all I need to look at in section 4. That was technically section 10.4. Let's move forward to section 10.5, where we actually find the areas of these polar functions. Now, if I remember correctly, on the final exam, the problem that we have for these, the graph is provided. So it won't be necessary to graph them, but I'm pretty sure that's correct. I did write the final, but it's been over a year. Um, Excuse me. Anyway, yeah, I feel like it's going to have the graph provided. I'm pretty sure I included that because I didn't want that to be a hindrance. I want us to be able to find the area. That's the big thing. Okay. But we'll talk about some of the strategies as we go. More than likely, I'm going to give you these types of graphs to find the areas of, rather than these types. Although we could take something like this and find the area of one petal and then multiply that by 4 because it does have symmetry. One of the great things about these polar graphs is that there is a lot of symmetry when we're using our sine and our cosine functions. And we can certainly use that to our advantage, like the cardioid here. The top half is symmetric to the bottom half. Or this one, the right half is symmetric to the left half. So we can certainly use that to our advantage in some scenario. Excuse me. Okay. Now, talking about the area inside a polar curve. And we'll have a polar curve defined by r equals some function of theta. The area is equal to integral from alpha to beta of 1/2 r squared d theta. And so this is our formula for the area. I don't think you need to memorize it, but it might be worthwhile just to memorize it. The understanding of why this formula works really won't come until we get to calculus 3. It's kind of unclear why we have the 1/2 r squared there. I could actually explain it a bit. It's based on the shape of area in polar coordinates. Because if we look at rectangular, if we have a length x and a vertical length sorry, I did it backwards. If we have a dx and a vertical component y, and then y dx is just the area here. We integrate the function with respect to x. Okay, that's our area. When you look at a polar segment, if you think about the area between, it's basically a sector of a circle. Okay, rather than being a rectangle, it's a sector of a circle. And so we have our d theta in between, whatever that d theta measures, and then our function r determines the curve. Now, if we think of the area of a sector of a circle, sector is this pi segment. No, I'm not talking about pi. I'm talking about pi for Thanksgiving, not pi for geometry. So it's like or slice of pizza, whatever you want to call it. It's almost lunchtime. We shouldn't be talking about food like that. Basically, it's lunchtime. So we have this arc and we have this region. Okay, So we know the area of the full circle is pi r squared, and d theta is just whatever fraction of pi that we have. But basically, let me see if I can draw this conclusion for us. Area of a sector is 1/2 r squared theta. Now, in this case, theta, we're calling d theta is whatever the delta theta, or whatever you want to call it, the differential between these two angles. Okay, and that's why it correlates directly to the sector of a circle. Just like over here, dx is more of a delta x, the distance between these 2 points. That's our connection. So that's why we have this formula inside, and then we go from angle alpha to angle beta, whatever alpha and beta happen to be. Okay, so we'll look at this from a slightly different way in Calculus 3, but yeah, that's our formula for the area. All right, key identities that we'll need to use. These are our power-reducing formulas, which we have used previously, and that says that sine squared of theta is equal to 1/2 times 1 minus sine 2 theta. Cosine 2 theta, my bad. And then cosine squared theta is 1/2 times 1 plus cosine 2 theta. We'll need both of those identities because when you think about plugging a function into r squared, we just have r equals 1 plus sine theta. We're going to square this sine, so we're going to have sine squared. And the only way that we can integrate sine squared, going back to chapter 8 or 7, whichever one it was, we had to use what we call our power-reducing formula because we can't integrate a trig function squared, at least not sine or cosine. So we convert it to where we have a linear cosine function, cosine to the first power, and that can actually be integrated. Those can actually be integrated, as well as the constant with it. So that's really the key right there that allows us to integrate most of these problems, is using these power-reducing formulas, or power-reducing identities. So let's use that example I just mentioned, r equals 1 plus sine theta. Let's just find the area inside. Okay, now I'm just going to make it real quick. And you can tell it's really quick because I'm just using multiples of pi over 2 now. Just to get an idea of where the points are. For this type function, this is usually sufficient. 0, we get 1. At pi over 2, we get 2. At pi, we get 1. 3 pi over 2, 0. And at 2 pi, we get 1. Okay. So very quickly, we can plot the graph. 1, 1, 1, 1. And we go out to 2 in this direction. So 1, 2, 1, 0, 1. Okay, so it is a cardioid. Does this number and this number match? Alright, so let's see. We can either integrate this from 0 to 2 pi, or we can go from like negative pi over 2 to positive pi over 2 and then double. It's probably easier to go 0 to 2 pi in this scenario. then we have 1/2 r squared theta, which means we can bring the 1/2 outside, and then our r is 1 plus sine theta, in parentheses squared, d theta. That's a d theta there, sorry. So we'll go ahead and square the binomial here. 1 plus 2 sine theta plus sine squared theta. And we'll have to convert sine squared theta into its corresponding power-reducing identity, which is 1/2 times 1 minus cosine 2 theta. And we might choose to distribute that 1/2 just so we can combine it better with the other terms here. So that would give us 1/2 on the outside, 0 to 2 pi, and then we have 1 plus 2 sine theta plus 1/2 minus 1/2 cosine 2 theta d theta. One and 1/2 is 3/2 plus 2 sine theta minus 1/2 cosine 2 theta. Now we can integrate each of these three terms. We couldn't do that with sine squared, but we can totally do that with cosine of 2 theta. Integral of 3/2 is 3/2 times theta. Integral of 2 sine theta is negative 2 cosine theta. And the integral of negative 1/2 cosine theta is negative 1/4 sine 2 theta. 0 to 2 pi. Notice that we can integrate cosine of 2 theta. Because of the 2 there inside the angle, we divide by 2 as we integrate, which took this 1/2 and made it a 1/4 on the outside. We integrated cosine, though, that is sine of 2 theta. Alright. Now we're ready to plug in our angles, 2 pi and then 0. So plugging in 2 pi, (3 over 2 times 2 pi would be 3 pi. Cosine of 2 pi is 1 times minus 2, minus 2. So this would be sine of 2 times 2 pi, sine of 4 pi is 0. Then we plug in theta equals 0, which would be 3/2 times 0, 0. Cosine of 0 is 1, so minus 2. And sine of 0 is 0. So let's see, this is 3 pi minus 2 minus a negative 2. Do those cancel? Minus 2 plus 2. Yeah. So those will cancel out. Is that right? Yeah, that's right. Didn't anticipate that happening. Okay. So the 2's cancel here. So we just get 1/2 times 3 pi, or 3 pi over 2 is our area. And that's kind of our basics for working through these area formulas. Let's look at some more of those. find the area of one loop of r equals 2 sine 2 theta. Fortunately for us, we've already plotted the graph for this once. We know our graph looks like this. I always draw that first one a little bit too big. Anyway, we get the idea. First one's like perfect, and the other three are like decreasingly accurate as we go. But we want the area of one of these petals. Now, the key here when we have these flower graphs like this is that when we want to find our limits of integration, we have to basically go from when it starts at 0 to when it comes back to 0. Okay. So when is sine originally equal to 0? Well, sine of 0. So this is theta equals 0. That's where we'll start. As far as where we'll finish here, it's basically pi over 2. Because 2 times pi over 2 is pi, and sine of pi is 0. Now, you'll look at the graph and say, well, yeah, this is the line for 0, and this is the line for pi over 2. Why is that such a mystery? Well, it depends, because the more complicated our graphs get, if this was 2 sine of 4 theta, it would be a little bit more of a challenge to figure out where that actually happened. But essentially, we know that the first 2 times that sine is equal to 0 is at sine of 0 and sine of pi. So it's a question of, okay, for what value of theta is this equal to 0, and is this equal to pi? And that's really what we're looking for. Okay. So we want our area. Let's see, we'll integrate. We have a 1/2, of course, from 0 to pi over 2. And we have our function r being squared. So 2 sine 2 theta in parentheses squared, t theta. So we'll go ahead and square everything inside. So it's 4 sine squared 2 theta. And the 4 we can bring out with our 1/2. 1/2 of 4 is 2. And then sine squared theta, we'll take that, we'll make it into 1/2, 1 minus cosine of 4 theta. Now, that's our same power reducing identity. What happens is, whatever angle is here ends up being doubled. So we said we had, on the last example, we had sine squared of theta, it became cosine 2 theta. Sine squared of 2 theta would become cosine 4 theta. Otherwise, the pattern is the same. And this 1/2 and the 2, those will cancel each other out. So we can just integrate this like it is. So it's theta, integral of 1 is theta, and minus 1/4 sine of 4 theta. 0 to 2 pi, or pi over 2. One thing I want to caution you about is that if I wanted the area of this entire graph, we wouldn't necessarily go 0 to 2 pi. And that's because some of these graphs, if we go from 0 to pi, we might get the whole graph, and then pi to 2 pi repeats. We might get the area twice. We don't want to do that. We just want the area once. That's why in a problem like this, if we just find the area of one loop, we can multiply that by 4 to get the total area inside these loops. And that might be a more efficient way of doing that. It's kind of a lot that we're trying to fit in here into one class, but I'm just trying to give you what I can in the time that we have. All right, so we plug in pi over 2, so we get pi over 2, and then 4 times pi over 2 is 2 pi, sine of 2 pi is 0. Plug in 0, we get 0, sine of 0, 0. So we really only got one value here, which is pi over 2. So the area of each petal is pi over 2. So multiplying that by 4 petals, then the area inside this curve is 2 pi. So we can think of either the area of one loop as being pi over 2, like we said, or we can think of the total area being 4 times that, because there's 4 petals, and that would be 2 pi. Okay. One last problem I want us to examine. Find the area inside r equals 2 cosine theta, and that is outside r equals 1. Now 2 cosine theta is a circle of radius or diameter 2 to the right of draw it. Radius 2. Ooh, my bad. No, diameter 2. Radius 1, diameter 2. It's not that hard. I'm making it hard. Okay. Something like that. Now, r equals 1 is a circle of radius 1 also, but centered at the origin. So it instead looks sort of like this. So here's r equals 2 cosine theta, and here's r equals 1. Now we want the area inside r equals 2 cosine theta that is outside r equals 1. So inside this circle, but outside of this circle, that will be this area right here that we're trying to find. Now, that means we need to figure out the point of intersection right here and right here, because that value of theta and this value of theta will be our limits of integration, basically. Now, the way that we find the points of intersection is we set the two functions equal to each other. So we would just say 1 equals 2 cosine theta. It's really the same strategy that we employed with rectangular coordinates. It's just happening in the polar plane instead. So we said 1 equals 2 cosine theta. So 1/2 equals cosine theta. And we look at where 1/2 is equal to cosine theta on like a unit circle or something. That's going to be theta equals pi over 3 and 5 pi over 3. Now, we would say this is pi over 3, but that's our ending value. Our starting value would actually be, instead of saying 5 pi over 3, we'll actually say negative pi over 3. Now, there is another course of action we can take here, and we know the top half of this area is symmetric to the bottom half. Okay, so we could just find this top half right here from 0 to pi over 3 and then double it to get the bottom half also. And that's probably the way that we'll go. So we want our area to be 2 times the integral from 0 to pi over 3 of 1/2 times r squared d theta. Now the nice thing here about doubling the area is that we cancel out the 1/2 that's natively part of this. Now, here's the other issue that we run into this example, is that we want the area inside one curve but outside the other curve. So we're actually going to have to get two different radius functions. We have our outer radius, and we have our inner radius. Now our outer radius is the one furthest from the origin, which would be our r equals 2 cosine theta, and the inner radius is the one closest to the origin, which is r equals 1. Now, we don't have to do this in two separate integrals. We can combine it to a single one because all the conditions are the same here. The 2's cancel out regardless, but the 1/2. Our limits of integration are identical, so we can think of it as 0 to pi over 3, and we'll take capital R squared, which is 2 cosine theta squared minus little r, 1 squared d theta. So we don't have to put that as two different integrals. We can do it all as one integral if we want, which generally is easier. Okay. I don't know if I have enough space here. Alright. So that'll be 4 cosine squared theta minus 1 d theta. Now, cosine squared theta, again, this is 1/2 times 1 plus cosine 2 theta. Now, this is also multiplied by 4. So 4 times 1/2, so it's actually a 2 distributed. So that'll be 2 plus 2 cosine 2 theta. We still have our minus 1 hanging around. Okay. And so we can combine our constants. That'll just be a 1 plus 2 cosine 2 theta. And so if we integrate, we get theta plus sine 2 theta. And again, we divide by the 2 when we integrate, so it's just sine and without a coefficient. Plugging in the values here, pi over 3, we get pi over 3 plus sine of 2 pi over 3. Now sine of 2 pi over 3 is root 3 over 2. Yeah. Minus, and if we plug in 0, 0 plus sine 0, 0 and 0. So our area is pi over 3 plus root 3 over 2. It ends up being a pretty strange value. We can't actually combine those together. If we wanted, I guess we could get a common denominator at least and write it as a single fraction, but that doesn't really get us much further, to be honest. So that we can just leave our answer like that. But that then describes the area of this whole region, top and bottom, that's shaded. And we found the area of 1/2, and then we doubled it. That's how we end up able to end up with this answer. So anyway, that's our last set of new material. On Thursday, if you have specific questions on the review, please bring them to the lecture and I can go over them during class time. Otherwise, I'm just going to go through and pick and choose, and I'll also be sure to tell you which ones you can skip. There's a few that we can skip that you won't need to worry about, and also that we didn't talk about anyway. But we've covered everything that's going to be on the exam. It's just that there is some extra stuff in the review that is not going to be on the exam. So. And if there is something on the exam we didn't cover, I'll just give you credit for automatically. So if you encounter anything like that, don't panic. Just keep going, and yeah, it'll be all right. Make sure you get those tests in to me by tomorrow night, Wednesday night. Again, if you didn't see the announcement, I did make it a take-home just to make up for the issues that Canvas was having this weekend, which is regrettable. I don't know why it chose to do that. I just could not get it to acknowledge any of the equations I entered and graph them or represent them properly. And I was very frustrated Sunday night when I was looking at that after everyone emailed me. I know y'all were frustrated too that we're trying to do the test. So I went ahead and just made that a take-home. And hopefully everyone will do better because of that, and that'll be good. We'll go into the final straw. So, anyway, if you do have any questions, send me a message, Canvas or email. But yeah, be ready to review on Thursday. Bring your questions so I can go over whatever you need me to go over. But yeah, essentially what we've done on each of our tests is basically what's going to be on the final, plus the things that we've talked about today with the area inside of a polar curve. That's really all that's going to be there. There's quite a bit of it, though. I mean, there's a lot, and if you look at the review, it's pretty thorough. So that should get you ready for it. Looking at your old tests, looking at the review, that should be a good way to prepare, I think. And if you want to go back and look at anything else, you can, that you feel that you need to work on specifically. So, all right, you all have a good rest of the day. And be sure to get everything done that you need to, and I will talk to you on Thursday.